All right, kids, we got some chemistry to do. Not a ton of chemistry, and it's not uh, it's not anything super crazy, but it can be a little confusing. I will do my best to explain it in as clear a way I can. I'm gonna use some analogies here that involve like cooking and baking. So if you're not a cooker, if you're not a baker, this might not be as simple. Um, this right? That topic right there. I know, big word, scary word. I'm gonna say it in a second. We're gonna make it make more sense. But that is the last new piece of information before the midterm. So these two pages, like this page of notes and these couple pages of examples. So 42, 43. There are even examples on 44. I'm not gonna mandate that everyone must do page 44, but the questions on page 44 are available if you want to do them for your own practice. Answers will be posted in the notes like they usually are. Now, this topic and this word right here, stoichiometry, right? That's how you say that word. Excuse me. Stoichiometry. Um, this is a fancy chemistry word. I was going to say physics. This is chemistry. This is a fancy chemistry word for ratios, right? It's about ratios and moles. Now you might notice something odd in this whole section, right, or all of this page. There are no blanks. There's nothing to fill in, right? That's not because Ms. Summers and I didn't want you to like listen and fill things in. Excuse me. It's because we have found that even though like these notes do go with it, it's easiest to try to do this while someone like me or someone like Ms. Summers kind of guides you through a few examples, and then we kind of let you do a few on your own, and it'll roll from there. I'm going to use some analogies that aren't exactly in the notes, but they'll work, all right? They fit. They fit well, in my opinion. All right, so these ratios come largely from having a balanced chemical equation. So we balanced chemical equations a little before the break. And I'm going to put in an example up here of a balanced chemical equation. And I'm going to use this as my first example, right? There's a second example, there's a third example. There are more examples to go through, but I'm going to use this as my first example, right? Now, let me write this a little bit offset like that. Okay. Right there is a balanced chemical equation. This is the combination, the synthesis of water through hydrogen and oxygen gas. Right? It's balanced because there are the same number of each element on both sides of the equation, the sides separated by the arrow. The big thing is about the balanced reaction is that we had said, or I had said before, I need two hydrogens, I need one oxygen, and that'll make two water molecules, right? You can think of this in terms of just literal molecules. So like H2 and H2, so two H2s and an O2. You can smash them together, you can combine them, and you can form two water molecules. And that works great. But it's not super practical for doing experiments. I don't want to have to isolate literal individual molecules in order to do a reaction. I would prefer to work with realistic amounts, and those realistic amounts are moles. So this bullet point right here, the second bullet point, I would put a star next to it, I would underline it and highlight it, do something for yourself. Because these coefficients that come before a compound or an element, and remember, there's a 1 here, they represent the number of moles of that element, of that compound, of that substance that you need in order to do this reaction. So I need 2 moles of hydrogen, I need 1 mole of oxygen, and that will create 2 moles of water. The reason that's particularly relevant is because it's also the only way that we can compare like how much of something do we need versus how much of something are we going to make. I had said before that these chemical equations are kind of like recipes. So like if you're making a cake or cookies or brownies, right? The recipe might call for 3 cups of flour. I don't know. I'm just pulling that out of the air. I don't actually bake. I'm not super good at it. Ironically, for a chemistry teacher, I don't particularly enjoy like exact measurements. I'd much rather kind of play with it. I like cooking better than baking. That's just me personally. But baking is really like superb chemistry because it's exact proportions, and when something goes wrong, you can often tell exactly why it went wrong based on what you started with, right? Say the recipe calls for 3 cups of flour, but you only have 1 cup of flour. You are not going to be able to follow the recipe perfectly the way it's written because it just wrote that you need 3 cups, but you only have 1 cup. You can still follow the recipe. You just have to make sure everything scales down correctly. You need to make sure that the ratios of each ingredient are still in the correct proportion. The stoichiometry still has to fit, right? Excuse me. So if you only have 1 cup of flour, but you really need 3, then what you might do is downscale everything by 1/3. Divide everything by 3, right? And that would keep all the proportions the same, right? The stoichiometry is about ratios and the proportions that we have, right? In our example, in the reaction that I just wrote down, right? For every 2 moles of hydrogen that I start with, I'm going to make 2 moles of water. For every 1 mole of oxygen that I start with, I'm going to make 2 moles of water, right? So it's a 2-to-2 ratio of hydrogen to water. It's a 1-to-2 ratio of oxygen to water, right? Knowing those ratios and knowing that they have to be exactly that much, right? Again, say I get like cookies, probably easier, right? If I need 3 cups of flour to make 2 dozen cookies, so 3 cups of flour would give me 2 dozen cookies. What if I wanted to make more than 2 dozen cookies? What if I wanted to make 4 dozen cookies, right? That's twice as many cookies as a recipe would normally make. That means I need to start with twice as many ingredients, right? How that analogy fits here, or metaphor, I guess. I didn't use like or as, so it's a metaphor. How that metaphor fits here is if I wanted to produce 4 moles of water, if I wanted to double the amount of product that I create, then I need to double each of these parts, right? I would have to double the amount of hydrogen that I had. I would have to double the amount of oxygen that I would have. It would still work because the ratios, the proportion, the stoichiometry, is still correct for a larger amount. Right? Similarly, if I only wanted to make 1 mole of water, I would have to halve everything. So I would need half as much of each thing. Right? And that's where we are here. I can predict or determine how much product is made or how much reactant is needed based on knowing the ratios, based on knowing those proportions. Right? So, looking at this first example down here, right? I'm intentionally not showing the next bit because I'm going to show you like a version that how I usually do it, right? So what I usually do down here. So let's look at this question that has to do with this balanced equation, right? How many moles of H2? So what I'm going to do is I'm going to find, okay, here is H2. This is one of the things that I'm dealing with. How many moles of H2 are needed to completely react with 2 moles of N2? All right, so N2 is the other thing I'm dealing with. Whenever you're doing stoichiometry, you'll notice that the question did not mention the word stoichiometry. It did not mention the word ratio. But it's asking you about how much of something do you need to do something else. Right? That's kind of your hint that a stoichiometry question. The fact that this was not mentioned by name, this is ammonia, it was not mentioned by name, it's not necessary, I'm going to cross it out so that I know don't use that compound, don't use those numbers. Right? Now, I said this is about ratios. In math class, one of the ways that you can display a ratio is by using a fraction. So I'm going to set up 2 ratios that have to be equal to each other. The reason they have to be equal is because I'm not allowed to change that proportionality. I'm not allowed to change the proportion. I can change how much I have, but I need to change it by the same amount. Right? So what I could say is that I have 1 N2 and 3 H2, right? This side, this part of my proportion, is from the equation. This is from the chemical equation that I have written it's already balanced, right? That has to be equal to whatever the question is asking me about. This question asks, how many moles of H2, right? So I don't know how many moles of H2 it is. So I'm going to call it X. It's X moles. It's some number that I don't know yet. Are reacting with 2 moles of N2. So I have 2 nitrogens. Right? Now that I'm here, now it's just math. I know that 1 over 3 equals 2 over X. And in order to solve for X, cross multiply and divide. And that's what ends up getting described here. Now, you'll notice that the way that I did it is slightly different. It's set up slightly differently from the way that it's set up in the example here. But just because the H's are on top and the N's are on the bottom doesn't change the answer. The answer is still 6. X still equals 6. Right? So you can set up the ratio whichever way you want as long as you're consistent. I put nitrogen on the top. The notes have hydrogen on the top. It'll work both ways. Right? I'm going to walk you through the first one, and then I'm going to ask you to do the second one. I'll go through it. Try the third one. I'll go through it. Try the fourth one. I'll go through it. And then there are some questions up on my CBA right now that I'd like you to also practice. I'll go over those first thing on next time there's a video. Next time you're in class, right? But let's look. So this question asks, how many moles of oxygen gas, so I'm going to stop there, I'm going to look for oxygen gas, here it is, are produced by the decomposition of 6 moles of potassium chlorate. All right, one of these two is potassium chlorate. It's this one, and I know that because chlorate is a polyatomic ion. It's found on table E. So this is why we had to do all that other stuff. I had to do naming. I had to do balancing. We had to do, all of those other things that we've done before are going to come into play now. Now, I never mentioned this middle compound, so I'm not going to worry about it. I don't use it. According to my equation, these numbers from the other side of the proportion were from the question. So I'll usually set it up like that. The first number, the first proportion that I'll have is from the equation. The second proportion that I'll have is from the question. And I'll set them equal to each other. So from the equation, KClO3. Well, there are 2 of those. And there are 3 oxygens. And that has to be equal to, I don't know how many moles of oxygen, that's what I'm solving for, but I have 6 moles of KClO3. Now, again, turn it into math. 2 over 3 equals 6 over x, which means that 2x equals 18, so x equals 9. It's 9 moles of oxygen gas that get produced. All right? I'm going to... Oh gosh. Please no. There we go. I'm going to move up here to number 2. I'm going to start walking you through it. I'm going to just tell you something about this, some of the phrasing here. I want you guys to try to set it up. Take a second or pause the video. I'll go through the answer. Try number 3. Pause the video. I'll go through the answer. Do the same with number 4. Right? So this question asks, how many moles of hydrogen gas, I'm not trying to cross stuff out here, hydrogen gas, are produced from 3 moles of zinc. Right? They keep going here. They give us extra information, right? They give us excess information. If you see excess, one of 2 things that you can do. 1, you can ignore whatever's about to be said because excess means it's extra information, right? An excess of something means I have too much of it. It's not going to factor in. It's not an exact number. It just means I have enough, right? So an excess of hydrochloric acid. The way that I worry about it, the way that I deal with it, is I know that automatically I can cross out hydrochloric acid. I can cross out HCl. That's an excess. But I need hydrogen gas, so I need to worry about this. and zinc, so I need to worry about this. This was never mentioned, which means it's unimportant to this question. Now I'll set up my proportions. 1 zinc and 1 H2. That's going to equal 3 zinc and X H2. And again, the reason for that, this side came from the equation, and this side came from the question. And my answer here, X equals 3. Right? Hopefully you paused the video, right? If you haven't paused the video, you haven't tried 3 and 4, pause the video now, try 3 and 4. I'll go through the answers now. Yeah, I'm guessing you're back. So, how many moles oxygen gas? 4 moles propane. Right? Here is oxygen, and here is propane. I know that because this is carbon dioxide, and this is water. So C3H8, I have 1 of those over 5 oxygen. That's from the equation. X moles of oxygen, 4 moles of propane. And if I do the math, X equals 20. Finally, I have potassium nitrate, how many moles? Potassium phosphate, how many moles? Right? So I have potassium phosphate here and potassium nitrate here. The aluminum stuff doesn't matter because we didn't ask about it. So 3 potassium nitrate over 1 potassium phosphate. Right? I don't know how much potassium nitrate the question is asking about, but I know exactly that they have 2 moles of this. And again, when I turn this into math, X equals 6. Right? Now, if you have more questions, if you want clarification, right, if you want more examples, let me know. Email me, find me 10th period, find me during lunch, ask me during class. We're going to do lots of review in the next few weeks. You're not going to see more questions on this other than the homework, right, the assignment that's up on my CBA. You're not going to see more questions on this until the practice test late next week, until the midterm, right? So I'm not going to quiz on just specifically this little topic, but you are definitely going to see at least one question like this on the practice test, at least one question like this on the midterm. I'm letting you know, all right? So if you are confused, if you want to know how to do it, if I wasn't clear enough here, please let me know. Otherwise, I will see you in the next video or next time in class, and we'll go through those practice questions that I assigned on my CBA. Until then, kids, take care. See ya.